Hi, my name is Emma and I'm the Chief Scientist at Izon Science, and today I'll be explaining the mechanisms at play that transport nanoparticles through a nanopore and how they influence your measurements. There are numerous different mechanisms which affect the transport of particles through micro and nanofluidic channels. Each has a different origin and form of the force that acts on the particle and results in its movement. In TRPS nanopore specifically, the three main transport mechanisms at work are hydrodynamic, electroosmotic and electrophoretic transport. The last two are part of the class of electrokinetic transport phenomena. These are a range of effects that are connected to a force acting on the electrical double layer, which forms at a solid-liquid interface. Let's now go through those three main transport mechanisms relevant for TRPS. Hydrodynamic transport is the result of a difference in pressure on each side of the nanopore. Due to this pressure difference, liquid will start to flow through the nanopore, similar to water flow in a pipe. The liquid in the centre of the pore moves the fastest, and slower towards the pore walls. We are talking about a parabolic flow profile. When we now put a particle in this flow field, a force will act on it. The force originates from the variation of the pressure and viscous forces on the particle surface. For the dimensions and applied pressures typical for TRPS nanopores, the particle follows the flow lines of undisturbed fluid flow and moves together with the fluid through the nanopore. In your TRPS instrument, the liquid in the lower fluid cell is open to the surrounding air, which serves as the reference for the pressure measurement. The total applied pressure is the sum of the pressure head in the upper fluid cell due to the liquid level of the sample and the pressure applied with the pressure system. Using the pressure system, you can increase or decrease the fluid and therefore particle flow, balance the intrinsic pressure head so no fluid flow occurs at all, or reverse its direction, making fluid flow from the bottom to the top of the nanopore. Next is electroosmosis. Electroosmosis is the motion of a liquid in an electrically charged channel induced by an electric field. Most materials acquire a surface charge when exposed to a liquid, and a so-called electrical double layer forms at the solid-liquid interface. Applying a voltage across a channel or pore results in a fluid flow parallel to the channel walls. The direction of the flow is determined by the sign of the voltage and the sign of the surface charge. Microscopically, the fluid flow is due to the mobile ions in the double layer experiencing a force due to the electric field and consequently dragging along the surrounding water molecules. So, the cause of the electroosmotic flow is the Coulomb force between the ions and the applied electric field. In a cylindrical channel, this results in a so-called plug flow, which means that the flow is approximately constant across the channel, apart from an area close to the double layer. The thickness of the double layer is characterised by the Debye length, which is in the range of nanometers for TRPS nanopores when used with the standard measurement electrolyte. For TRPS nanopores, which are negatively charged, the electroosmotic transport in the standard configuration, which means a positive applied voltage and pressure, is therefore in the opposite direction of the hydrodynamic transport and slows the particles down. The magnitude of the electroosmotic transport depends on the charge of the pore material, or more specifically the zeta potential, the strength of the electric field at the pore walls, and the electrical properties and viscosity of the solution. The effect is more pronounced in smaller nanopores, where higher voltages are applied, and the electric field gets more concentrated in the pore itself. It is generally an unwanted effect for TRPS and can prevent particles from entering the nanopore under certain circumstances. Last is electrophoresis, the transport of a charged particle under the influence of an electric field. Microscopically, it has the same cause as electroosmosis. Again, a double layer forms at the particle surface, and due to the applied electric field, a Coulomb force exerts a force on the ions. So, the force is not actually applied directly to the particle, but to the ions in a diffuse layer located at some distance from the particle surface. It is then transferred to the particle surface through viscous stress, which results in the movement of the particle. In a standard TRPS setup, this means that negatively charged particles in the upper fluid cell are pushed downwards through the nanopore towards the positive electrode in the lower fluid cell. As with the electroosmotic transport, the magnitude of the electrophoretic transport depends on the strength of the electric field around the particles, the electrical properties and viscosity of the solution, but also the zeta potential of the particle instead of the nanopore. All transport mechanisms combined determine the flow and velocity of particles passing through the nanopore. This is reflected in the rate and the duration of the resistive pulse signal. The relative strengths of the transport mechanisms at play depend on the pore dimensions, the applied voltage, pressure, and particle properties. A correct choice of measurement parameters is crucial to obtain accurate results with your TRPS instrument. For example, for a concentration measurement, a dominant hydrodynamic transport is of advantage, which is generally the case for microscale pores. On the other hand, for a charge measurement, a high electrophoretic component on the overall transport is desired. Also, a compromise between the particle rate and the duration of a particle translocation must be found in order to ensure a reasonable sample throughput, while at the same time acquire sufficient number of data points per translocation. This might all seem very complicated at first, but you don't have to worry. Izon has developed measurement methods like the multi-point concentration measurement or the zeta potential measurement using a multi-voltage calibration. These methods correct for the different transport mechanisms and automatically take care that you get the correct results. So as long as the user follows the standard procedures as recommended in the user manual and implemented in the Xoid software, a good result will be obtained. However, a good understanding of the transport mechanisms involved is recommended in order to troubleshoot issues and be able to better interpret the results. In the world of micro and nanofluidics, additional transport mechanisms can play a role and are often used to move particles around. To complete the discussion, some of those are named here. For example, dielectrophoresis, which occurs when a polarizable particle is subjected to a non-uniform electric field. The particle does not have to be charged but must have different dielectric properties to the surrounding medium. Calculations show that a small dielectrophoretic force exists at the pore orifice of the smallest TRPS nanopores. However, it is much weaker than the main transport mechanism and can therefore be neglected in a usual setup. Particle movement due to gravity, diffusion, or due to a streaming potential are also orders of magnitude smaller than the main transport mechanisms mentioned above. To summarise, hydrodynamic transport, electrophoresis and electroosmosis are the key transport mechanisms at play inside your nanopore during a TRPS measurement. Understanding how each of them interacts with your particles will help you get the most out of your TRPS system. If you have any questions, please contact us at support@izon.com. Thank you.